So that was all informational. Now we're going to actually get into what do we do with this information and how does it work for us. So first, a quick warm-up. Nucleus of californium contains 98 protons and 154 neutrons. Which of the following correctly identifies the nucleus of californium? Ready? Ready? 98 protons, 154 neutrons. Neutrons plus protons, that's your top number here. So it's this guy, right? Whoa, whoa, whoa! Alright, remember this? Last video, if not. Next up, an unstable nucleus sheds alpha particle. Helium nucleus made from 2 protons and 2 neutrons. Protons and 2 neutrons. So that's what's happening here. We have our parent nuclide. That's the sample that we start off with. And then radiation happens. And there's not a better way that I know of to tell you about radiation happens, because if I think of something better, then you're going to miss the point. Remember that radiation is spontaneous, and it can happen at seemingly random intervals. Sometimes if you're rolling the dice, you get that 1, or sometimes you get a 6. Just doesn't matter, it's completely random. So it's spontaneous. Happens abruptly for no apparent reason, and it's completely random. Okay? So we start with our parent nuclide. Radiation happens, and we get a daughter nuclide, which is the nucleus that is created, and then the stuff that is spit out. In this case, the alpha particle, the helium nucleus. Helium, remember, is 2 protons and 2 neutrons. 2 protons down in the bottom number, 2 plus 2 equals 4 up in the top. For the daughter nuclide, for our proton number, we're going to subtract 2 from that. That's going to allow us to determine what this element is. Then, to figure out which isotope it is, we're going to subtract the number of protons plus neutrons from the mass number. So let's complete the missing notation. Go ahead and try it out for yourself. All right, here we go. 238, 92, uranium. It's a thallium and an alpha particle, a helium nucleus. So first thing I want to do, thallium must be, without even using a periodic table, thallium must be atomic number 90, because 92, 2. This arrow you can think of as an equal sign. 90 plus 2 equals 92 on the right, 92 on the left. We're good there. 238 minus 4 should give us 234. 234 plus 4 is 238 on the right, 238 on the left. We're good. Alpha decay. Predict what's going to happen over here. Well, I mean, it's alpha decay slide. We're working on alpha decay. It's probably going to be an alpha particle, right? 4, 2, alpha. We know that because 88 to 86, that means this has to be a 2 over here. 222 to 218 has to be a 4 right here. 208, 84, and it's alpha emission. So this is going to be 82, and this is going to be 204. Get the hang of it? It's that easy. Okay. Particle physics primer. We have matter, and we have something other than matter. So an example of matter would be a proton or an electron. These are both matter. They're classified as matter. we have something else called antimatter. Antimatter is just like the matter, but something is opposite. Typically, that something is going to be your charge. So a proton, we would say, has a charge of +1, and an electron has a charge of -1. We can also put the mass number here up top. The mass of a proton would be 1. The mass of an electron, because it's so small, would be 0. We can do this for a neutron too. The mass of a neutron would be 1. It's got mass. The charge of a neutron is going to be 0. So we can do this for all of these different particles. This is what we talk about when we get into particle physics, but understanding this little bit here is going to help us have a better whole picture of what's actually happening. So we have this matter. The antimatter version of a proton would be it still has mass, but the charge is -1. This would be an antiproton. An electron, mass is the same. The only thing that's different is the charge becomes +1. This is an anti-electron. Is an anti-electron the same thing as a proton? No. Proton has a mass of 1. This has a mass of 0. It's not the same particle. It's the same particle as an electron, but the charge is different. Neutron. The mass is still going to be 1. The charge would be 1. So an anti-neutron, if you want. And you can do this for any of the particles. These are the 3 that we know right now. Let me introduce to you a 4th particle. This 4th particle has a mass of 0 and a charge of 0. So we don't even write these numbers for this. And this is called a neutrino. Neutrino. Small, fast, no charge. So we know the proton is a positive charge. We know the electron is a negative charge. Neutron has no charge. Neutrino also has no charge. Notice the neutr prefix. So it's neutral. But there's no mass to it. There's mass to it, but it's so small that it is negligible. And it moves really, really fast. At one time, it was thought that these particles went faster than the speed of light. Not the case. If it was the case, then that would be an exciting time, and physics would be broken. So what's our antimatter equivalent of a neutrino? Still 0, 0. But it's an antineutrino. This neutrino and antineutrino, these are the short words for this. The whole actual name for it could be an electron neutrino or an anti-electron neutrino. And we have a symbol. So for protons, we use the symbol P. For electrons, we usually use the symbol E. And for neutrons, we use N. Neutrino, we use V. Sub E, electron neutrino. If it's an anti-particle, then it would be a P with a line over it. If it's an anti-electron, then it would be an E with a line over it, neutrino, N with a line over it. Guess what an antineutrino is? VE with a line over it. Some context going forward.